Hi, my name is Muhammad Khairi Makhtar. We are going to design arithmetic logic unit that stands for ALU, that is part of the reduced instruction set architecture, which is RISC-V. In our ALU design, it will consist of multiplexer, arithmetic unit, and register. I will talk about for one multiplexer. A 1-bit for one multiplexer has two control signals and 4 inputs. The 4 inputs I0, I1, I2, I3 will connect to an AND gate respectively. For the control signals, S0 will connect to the second and fourth AND gates, and not S0 will connect to the first and third AND gates. For S1 will connect to the opposite of S0 connected. Finally, the output from all the 4 AND gates will connect to an OR gate. After all the gates are connected, we need to run the circuit. If it doesn't have any problem, we will press the file and press create update. Then we press create symbol file for the current file to create the for one multiplexer gate and save it. To build a 4 bits for one multiplexer, we need to insert the block symbol of 1 bit for one multiplexer that we made previously and connect to the circuits which have 5 inputs. We connect the I03 to I33 respectively and S0 to the first multiplexer. Continue the following step with the change of the inputs to I02 to I32 and S11 to the last multiplexer. The most important step is to label the bus line of the inputs correctly, and the outputs will be Y3, Y2, Y1, and Y0 respectively. We will get the output of Y3 to 0. We will do the same step and create the symbol for the 4-bit for one multiplexer.
My name is Ali Alfian bin Zainuddin. I'll be showing you how to create an arithmetic unit to be able to perform addition and subtraction for our 4-bit data input. A full adder consists of 2 data input A and B with a carry input. This produces 2-bit output which are carry out and sum. Based on the truth table of full adder, we can get is logic expression C out is A and B, or A and C, or B and C. While sum is A exclusive or B exclusive or C. We can proceed with the same method previously with the multiplexer by exporting these two block diagram. We can still create a 4-bit adder and a 4-bit subtractor separately. However, it will lead to using more logic gate. We create a 4-bit adder subtractor for a lesser logic gate. Create a new block diagram and add a full adder in our circuit. Since our data input A has 4 bits, we will name it as A30. Create a bus line connecting to input A at each full adder and name each line A0 to A3. For our 4-bit B input, we are connecting each of it with a carry in input through the exclusive OR gate. So when carry is in O, this ALU performs subtraction between A and B. If it's 1, addition is performed because of NOT gate at the beginning of C in input. Connect the output for each exclusive OR gate to the full adder at input B at each adder. Then connect the C out from the first adder to the second adder. Do the same with the next C out and connect every sum to S3 to 0 using the bus line. But we can ignore the final bit carry out signal in the adder, and lastly export this block to our block symbol also.
Hi, my name is Muhammad Hasif bin Muhammad Amran. Now, let's look at how to design for a register. We need to have 3 inputs, which are D3 to 0. Next is for clock and reset. Because of we have 4-bit input, so we need to have 4D flip-flop that we need to use in this register. We connect all the input D into D flip-flop by using a bus line and label all the line with their respective number. But all the clock and reset are connected together with their respective circuit into the flip-flop. We can connect all the output from flip-flop together using the bus line and label it as Q3, Q2, Q1, and Q0. We can combine them with an output 3 to 0. We export this to a block symbol also. We can combine all the things together to build a ALU design. So now we will try to run our waveform. I already analyzed and synthesized it. Now we can go to file to create a new university program VWF. Now we can find bundle finder and list. So these are all our inputs and output. Then press OK. We can look here, these are our inputs and output. I already put the value in, and now we try to run it. Here are the outputs for the ALU. For this input, it will come out with this output. When the reset is 0, there's nothing happen. So you can see here it's 0, 0, 0, 0. So when the reset is 1, it will got the correction happen and work with the clock. When the clock is at positive edge, so it will get the value. So when the edge selector is 1, 0, which means it choose A2, that is 0, 1, 0, 0. And we also see for the selector B is also 1, 0. We also choose B2, which is 1, 0, 1, 1. Now we see for the ALU OP, when the ALU OP is 0, we will subtract the value. When it's 1, we will add the value. So here is 0, we will subtract the value, which is A subtract B. So 0, 1, 0, 0 subtract 1, 0, 1, 1. We will get 1, 0, 0, 1. So that's all from our group presentation about the ALU design. Thank you.